Hey guys, Mrs. Thompson here, and today we're going to cover atomic orbitals. Before we do that, we need to talk a little more about the quantum mechanics behind this, and we're just going to barely touch on this. In 1924, Louis de Broglie, and that's French, so I'm not saying that quite correctly, just took Bohr's model of the atom and said that there's more to it. And what he found was a relationship between wavelength and mass. And he said that since an electron has mass, it also has wave-like characteristics. And so it's both behaving as a particle and a wave. The difference here is that he found that mass is inversely related to the wavelength, which means that the bigger the mass, the smaller the wavelength, or the smaller the mass, like a very small electron, the bigger the wavelength. Another important person in quantum mechanics is Heisenberg. And so Heisenberg has the Heisenberg uncertainty principle. And he said it's really impossible for us to know both the velocity and the position of the electron at the same time. And that's because as you try to measure it, you're going to change one of those things. You're going to add a little bit of energy as you try to figure out where it's at or how fast it's going. Then we move on to Schrodinger, and Schrodinger did some very complicated math, way beyond what we're ever going to do, and he came up with a wave equation which treated the electron like a particle, and he found within 90% probability of where the electron may be. And so what he came up with, orbitals, which are different than orbits around the nucleus, like Bohr's model. These are in an electron cloud. They're a region in space where there's a 90% probability of finding that electron. Okay, as we learn more about atomic orbitals, we have to learn about how to explain where they're at. And so the first thing we have here is the principal quantum number n. It's the major energy level that it's located in. And so if we can think back to simplify this in terms of the Bohr model, the n would be the shell that it's currently located in. And so we had this shell, which would be n equals 1, the first shell. The second shell, n equals 2. Third shell, n equals 3, and so on. Right. Within those shells, you have sublevels. And so it says electron energy levels within a principal energy level. So these are going to be our shapes, and I'll show you what I mean by that. The n number can tell me how many shapes are held within that principal quantum level. I will explain that a little later. All right, so let's get into the shapes that were found based on Schrodinger's equation. The first one is the s orbital. Okay, and that shape, here's what it looks like. It looks like a big ball. We're going to call that a sphere. So it's spherical in shape. And the number of orbitals that are associated with this sphere, if you see the picture, there is one orbital that looks like this. And the number of electrons that can go in that orbital is 2. And that's because every single orbital can hold 2 electrons. Okay, our second shape are the p orbitals. They go in 3 dimensions. We have 3 of them. One that's on the x plane, one that's on the y plane, and one that's on the z plane. And remember, these are determined by Schrodinger's equation. Okay, we call these shapes a peanut because it looks like a peanut. All right, the number of orbitals, we had 3 shapes there, 1 in each plane. The number of electrons, well, it's 2 electrons per orbital, and we have 3 orbitals, so that's 6 electrons. Okay, for the d orbitals, these look like this. There are 5 different ones, and they're in different directions. Most of them look like double peanuts, and except for this strange looking one at the end. But we're going to call this one double peanut, right? So you can recognize it when you see it. There are 5 of them, and the number of electrons that go with it would be 2 times 5, or 10. All right, the last shape, those are the f orbitals. Those look kind of like flowers down here. These, not so much. That looks like some strange node configurations, but we have 1, 2, 3, 4, 5, 6, 7 of them. Okay, we're going to call them flower, just so you can recognize them. and there are 7 of them, which means we would have 14 electrons within those 7 orbitals. I'd like you to memorize this order, S, P, D, F. That's something very important that you'll need throughout all of our electron configuration notes. So you need to know S, P, D, and F. You also need to know that the number of orbitals associated with those go in a pattern as well. 1, 3, 5, 7. So by odd numbers. Okay, now we're going to look at the relationship between energy levels and the number of sublevels that that energy level contains. Okay, so we're going to look at the first 4 energy levels. So when n equals 1, n equals 2, 3, and then 4. Okay. So it says here that the number of energy levels tells you how many sublevels you have. Okay, so then if there's 1 energy level, then you have 1 sublevel. In the second n equals 2, we have 2 sublevels. When n equals 3, we have 3 sublevels, and when n equals 4, we have 4. Then we're going to figure out which sublevels. And so they're first named by the energy level that they're in, and then the shape. And so in the n equals 1, we have 1 sublevel, that's the 1s. In n equals 2, we have 2 sublevels, that's the 2s. And then if we memorize SPDF, the next one would be 2p. In the third energy level, we would have 3 sublevels. We would have 3s, 3p, and then next would be 3d. In the fourth energy level, we would have 4s, 4p, 4d, and 4f. As you move on into the 5th, 6th, 7th, it just goes in alphabetical order. You don't actually have to use them, but if it gets into the excited state, you could. All right, so we're going to take some time to go over those and with practice questions. So the first one, how many electrons can go in the third principal energy level? So I have both of these charts here to pull information from. So it says third energy level, so that's when n equals 3. There would be 3 sublevels. We would have 3s, 3p, and 3d. Now this is saying in just that third energy level. So I'm going to look to see how many electrons are in each one of these. So in the s sublevel, I have 2 electrons. In the p sublevel, I have 6 electrons. And in the d sublevel, I have 10. So in total, in that third energy level, I have 18. Okay, for number 2, how many orbitals are there in the 3D? Okay, so I'm specifically talking about the third energy level, d orbitals. So just specifically talking about this. I'm not talking about the third energy level, just this sublevel. Well, in every d sublevel, there are 5 orbitals and 10 electrons within those orbitals. So for D, we would just say 5 orbitals. All right, number 3, how many orbitals are in the second principal energy level? So that's when n equals 2. And when n equals 2, we have 2 sublevels, 2s and 2p. What orbitals are in there? Well, in the s for spherical, we have 1 orbital. And the 2p, we have 3 orbitals. So that's 1 plus 3, or 4 orbitals altogether in the second energy level. All right, number 4, how many electrons can go in a 3s? So now we're specifically talking about the third energy level s. Okay, it could say 4s, it could say 1s. In the s orbital, we can only put 2 electrons. That's the answer to that one. Number 5, how many electrons can go in a single orbital? So in one orbital, you can put 2 electrons. Number 6, list the sublevels in the fourth principal quantum energy level. So we're looking at the fourth energy level when n equals 4. We're going to list them. So it would be the 4s, the 4p, 4d, and 4f. Okay. The next part of this, we're going to draw orbital diagrams. And so what the orbital diagram does is it describes how the electrons arrange themselves outside of the nucleus. And there are a few rules to go with it. First rule, the Aufbau Principle. The Aufbau Principle just means to build up. And so just means that we're going to start from the bottom, the lowest energy level, and then we're going to add electrons into the next higher energy level until we get further and further away from the nucleus. So it just means electrons fill the lowest energy orbitals first. Okay, the filling order for these electrons isn't how we would assume that they are. They don't go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p. They don't go in this order. Instead, they do this strange filling order because of an overlap in energy. So what ends up happening is the 4s actually takes less energy to add an electron to than the 3d orbital. And so electrons are placed in the 4s before they're ever placed in the 3d. And so this is a little chart to help you figure out what order they're placed in. This is written exactly as we wrote it in the table, with the exception of there's more orbitals. And so you would just do diagonal lines to figure out which order that is in. Rule number 2, Pauli exclusion principle, it just states that orbitals can only hold 2 electrons, which we've already stated. But now we need to know that they're going to spin in opposite directions, and that's just to overcome the repulsions that are happening between the 2 negatively charged electrons. When we draw electrons within an orbital, we use arrows to represent their spins. So we would put one up spin and one down spin, or one up arrow and one down arrow. I'm going to ask that you draw the up arrow first every time, or draw the down arrow first when you're drawing them, and that'll come into play in just a moment. All right, third rule is Hunds Rule. Hunds Rule just states that within a sublevel, you're going to place 1 electron per orbital before pairing them up. And that is because the electrons are repelling each other, and they would rather be in different orbitals if they can help it. The first rule, the Aufbau Principle, pretty much rules them, so they would rather be in the same orbital with another electron than move to a higher energy level. So these 3 orbitals have the same amount of energy. These all belong to, let's say, the 2p orbitals. Okay, since they have the same amount of energy, they would rather be in a separate orbital. And so that's why I've asked you to draw them up first before ever drawing them down. That's kind of like the empty seat on a bus rule. If you can see that there are some empty seats right here, you don't sit yourself next to a person, you go to the empty seat. Okay, same thing for electrons. So in these 2 drawings down here, this one is right and that one is wrong. Okay, we'll do a few examples. Here is my basic structure for filling orbitals. And so we're going to put our electrons into what we call like an electron hotel. We start on the first floor and then we continue to fill upward according to the Aufbau Principle. All right, so we have 3 electrons for lithium. So we'll start with the up arrows and then we'll add a down one. So we've paired them together because they'd rather be in that first energy level. So there's 2 of the 3. Now we just have 1 more, and we're going to go ahead and put it in here. What we're doing is we're putting them in their ground state, their lowest possible energy state. Oxygen has 8 electrons, so we'll start at the bottom, 1, 2. Now I have 6 left. There's 3, 4. We're going to put them now in the 2p orbitals. Start with up first in each of the separate orbitals. Okay, that's 3 of the 4, and then we have 1 more, and that one's going to go down. I've used up all 8 electrons. Notice these 2 are not paired up. Okay, we put them up first in each individual orbital, and then we start pairing them. All right, so we'll try 1 more silicon. Silicon has 14 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, that's it for atomic orbitals. We'll learn more about electron configuration next time we have notes.